Right, so we have the 11th question. Coming to the 11th question, it is function f is defined by y is equal to f of x, where x is equal to 2t minus mod of t, y is equal to t square plus t into mod of t, where t is a real number. Draw the graph of f for x from minus 1 to 1. Also discuss its continuity and differentiability at x is equal to 0. So let's go ahead with this problem step by step, please.
Okay, so we know that x equals to 2t minus mod of t.
Right.
Okay, so we know that t belongs to R. So to proceed ahead, we need to resolve this modulus function before.
Of course.
Okay, so the critical point is 0. So we'll split this at t equals to 0. So we know that x equals to 2t minus t for t greater than or equals to 0, and x equals to 2t plus t for t less than 0.
Right.
So x equals to t for t greater than 0 and x equals to 3t for t negative.
Perfect.
Okay, so since we know that t is greater than 0, so x equals to t, whenever we need to find the domain of second function, we need to check the range of the first function. Okay, so t is greater than 0 and x equals to t, so x will also be greater than 0.
Yes.
Similarly, t is greater than 0 over here, so x will also be t is less than 0 to be corrected.
Right.
Over here, so x will be less than 0 over here.
Exactly.
Okay, so now we know that for this part, when t is greater than 0, x will be greater than 0, and when t is negative, x is also negative.
Okay.
Now we have a function which is y equals to t square plus t times mod t.
Yes.
Okay, and segregating both the parts, I will say that in this part t is already positive, so this resolves to t square plus t square, which comes out to be 2t square.
Exactly.
Whereas this part comes out to be t square minus t square. So y is a constant function whenever t is negative.
Y is a constant function.
Exactly. And when t is positive, we get a function y equals to 2t square.
Yes.
Now what we have to draw is we have to plot the curve y equals to fx. Okay.
Okay.
So when we have to plot the curve as y equals to fx, but over here we have variable y equals to 2t square. So we need to transform this variable.
Yes.
And from the initial we knew that x equals to t.
Yes.
So we'll use this and replacing t by x.
Totally.
So we get y equals to 2x square.
Exactly.
Where we know that x is also positive.
Yes.
And over here y equals to 0 for x is negative. Okay, so moving ahead, we can say that y equals to 2x square and y equals to 0 for x negative and for x greater than equals to 0.
Yes.
So before plotting graph, we always need the function. So the previous steps led us to this function. Now since we directly have the curve, and which is a very simple function, we can directly use it to plot the curve. Okay.
Okay.
So we know that 2t square, so it will be a smooth parabola over here.
Indeed.
And it will be 0 for x negative. So this is the curve we have. Okay, so now we have to check the continuity and differentiability at x equals to 0.
Yes.
Looking into the curve, we can say that at x equals to 0, it's a continuous function. Okay, now we have to comment about differentiability.
Yes, so do we differentiate y is equal to 2x square at x equals 0?
Exactly, because we have proved that it is a continuous function.
Right.
So we won't be applying the first principle over here. We'll be directly differentiating it.
Exactly.
So f dash 0 plus will be 2x square d by dx,
which is 4x,
and we apply x equals to 0 over here,
which becomes
0. And similarly, f dash 0 minus is equals to 0 as function of for function of x for x negative is already a constant function, and when differentiate a constant function, we get its derivative equals to 0.
Exactly.
Since f dash 0 plus equals to
f dash 0 minus,
exactly,
which is also finite,
which is a finite value, we can conclude that it's a differentiable function.
Brilliant. So basically, let's just again take a quick recap over here. the function was given, and we were to draw the graph of the function from -1 to 1 of x, and also we had to discuss the continuity and the differentiability. So what we did over here was a methodical process. We finally found out, we removed the moduli, and we found out a function for y in terms of x and not moduli of x. Once we did that, we were very easily able to plot the graph, and when we plot the graph, it was pretty obvious for us that this particular function is continuous at this particular point x equals 0. And after that, once it's continuous, we hadn't had to apply the first principle. We just had to differentiate the particular function at x equals 0 from both the sides, and also make sure that the differential is a particular is a definite number, right? So we found out that f dash of 0 plus is 0, f dash of 0 minus is 0, and 0 is a finite number. So at the end of the day, f of x is both continuous and differentiable at x equals 0. So this was question number 11. So we have the 12th question here, which says f of x plus y is equal to f of x, f of y, where x and y are real numbers. So f of x is given to be 1 plus small gx into capital Gx, where limit of x tending to 0, small gx is equal to 0, and limit of x tending to 0 of capital Gx exists. Right. So now we have to prove that f of x is continuous for x belongs to R. So what condition do we need to prove that so that we can show that f of x is continuous for x?
First we will go through what we have been given with. Since given that limit x tends to 0, gx is 0, so it actually means that limit h tends to 0, g of 0 plus h equals to limit h tends to 0, g of 0 minus h equals to 0.
True.
Similarly, we have been given that limit x tends to 0, capital G of x exists, okay?
Right.
So we can say that limit h tends to 0, g of 0 plus h equals to limit
h tending to 0,
g of 0 minus h. Okay.
Exists.
So now moving on ahead with this question, we need to prove that fx is a continuous for x belongs to R.
Yeah.
Okay. So when will fx be continuous function? So fx will be continuous function when f of x equals to limit h tends to 0, f of x plus h equals to limit h tends to 0,
f of
x minus h.
Right.
Okay.
As per definition, right?
Yeah, exactly. So now moving ahead, first we'll check out our right hand limit, which states that limit h tends to 0, f of x plus h.
Okay.
So, but we know that the function rule that has been given to us states that f of x plus h equals to f of x into f of h.
Right.
Okay, so now I'm going to use this property in this given limit.
Okay.
So it becomes limit h tends to 0,
f of x into f of h.
f of x into f of h.
Right.
Okay, since f of x will be a constant function, so it becomes f of x into limit h tends to 0,
f of h.
f of h.
Right.
Okay, so now moving ahead, f of h equals to 1 plus g of h into capital G of h.
Exactly.
That is given. This is given in the question.
Right.
So now I am going to apply this in this above step.
Okay. F of x, limit of h tending to 0, 1 plus small gh, capital Gh. Right. Awesome.
Exactly. So now when I take the limit inside, it becomes f of x into 1 plus limit
h
tending to 0, g of h into limit h tending to 0, capital G of h.
Right. So we know limit h tending to 0, small g of h is already equal to 0.
Yeah, exactly. This value is 0, and this is a constant value.
Right.
Okay, so we know that the overall limit will become 0.
Yes.
Okay, so when I apply the limit, it becomes fx.
Of x. Yes.
Okay.
Right.
Similarly, when we solve, we can prove that limit h tending to 0, f of x minus h equals to fx.
Yes.
By above same procedure.
Right.
So we can conclude that left hand limit equals to right hand limit equals to value of function which is fx. So we
Right.
have actually proved that it is a continuous function for all x belongs to R.
Exactly. So this was the condition which we needed to prove, that LHL equals RHL equals f of x, the value of f of x. So let's just recapitulate the question again, and yes, so we were asked to prove that f of x is continuous for all x belongs to R. So we had two given conditions over here. One was that limit small g of x as x tends to 0 is 0, and limit capital G of x as x tends to 0 exists. So we used a few identities such as f of x plus h is equal to f of x f of h, and finally we derived at the fact that the left hand limit, which is f of x minus h as limit h tends to 0, is equal to the right hand limit, which is limit of f of x plus h as h tends to 0, is also equal to f of x at all points of time. So hence f of x is continuous throughout R. And this is question number 12. So the 13th question says, let a1 equals a0 plus b0 by 2, a2 equals a1 plus b1 by 2, and so on and so forth till an plus 1 equals an plus bn by 2, and b1 equals root of a1 b0, b2 equals root of a2 b1, and so on till bn plus 1 equals root of an plus 1 b1. Right, so we have a series of interrelated equations, and we are asked to find the limit as n tends to infinity of an and as well as bn. So clearly we cannot just substitute the value of a0 and b0 as infinity, right?
Exactly, and since we have to find limit n tends to infinity of an,
Hmm.
first we'll have to resolve what exactly is an. We can't just directly start solving over here.
So how do we get to know as to what we have to substitute?
Since we can see that all a1, a2, an and b1, b2, bn are relationships depending on a1 and an and bn, ar and br in other ways. Okay.
Right.
So what I'm going to do is I'll introduce a relationship between these two variables for our simplifications.
Okay, let's go ahead.
Okay. So I'll take a0 equals to b0 cos theta. So this gives us a relationship between both the variables, which is being handled by the parameter cos theta.
Right. Perfect. Okay.
Okay, so now moving ahead, we have been given that a1 equals to a0 plus b0 by 2. Okay, so now I substitute this thing and I get
b0 into 1 plus
cos theta
whole divided by
2, which comes out to be b0 cos square theta by 2.
Right.
Okay.
This is by the identity that 2 cos square theta is equal to 1 plus cos 2 theta.
Exactly.
Yes.
And now when I go on to b1, it is actually a1 b0's whole root. So again, when I substitute this thing, it becomes b0 square cos square theta by 2 whole root.
So a1 is substituted by b1 cos theta.
A1 is substituted by b0 cos square theta by 2 that we have already found out in the previous step.
Right. Perfect.
Okay.
So the previous step we just substituted and we got right.
Exactly, and we get
b0
cos theta by 2.
Right.
Similarly, moving ahead, we find out a2, which is nothing but
a1 plus b1
a1 plus b1 by 2.
Yes.
And similarly, if substituting, we can resolve it into b0 cos theta by 2 into
1
cos
plus
square theta by 4.
Right.
Okay. Similarly, when we substitute b2 equals to root of a2 into b1, we get b2 equals to b0 into cos theta by 2 and multiplied by cos theta by 4.
Yeah. Okay.
So now we can see that
A
a trend
pattern.
is being
Yes,
followed in
right.
all the series. Okay.
True.
So when we say that we have to find the value of an by observing the trend, we can say that an equals to b0 cos theta by 2 cos theta by 4 cos theta by 8 so on till cos square theta by 2 raised to n. We can see that in an the last term has this square term in it.
Right.
Okay, similarly, when we check out bn, we get bn equals to b0 cos theta by 2 cos theta by 4 so on till cos theta by 2 raised to n. And we
Perfect.
can see that the degree of the last term is 1 over here. Okay.
Right.
So now moving ahead, we will use one important identity from trigonometry, which is cos theta, cos 2 raised to 1 theta, so on till cos 2 raised to n theta. All these terms are in multiplication. This
Right.
gives us sum equals to sine 2 raised to n plus 1 theta into divided by sine theta into 1 by 2 raised to n plus 1.
Okay, so this is one identity which we have to remember.
Exactly. And now I'll tell you a shortcut to remember this identity.
Okay.
We can see that the number of terms over here are n plus 1.
Yeah.
So this 2 raised to n plus 1 denotes the number of terms over here. The degree denotes the number
okay.
of terms over here.
Okay.
This is the smallest angle.
A smallest angle.
And this one is the twice of largest angle.
Okay.
We had 2 raised to n over here, so we'll have 2 raised to n plus 1 over here.
Right, I get
Okay.
it. So this is a good way to remember. Yes.
Exactly.
Uh-huh.
So when we apply this identity in the given expressions an and bn, we can simplify an equals to b naught times cos theta by 2 raised to n sin theta whole divided by sin theta by 2 raised to n, and
Right.
simultaneously we can find that bn equals to b naught sin theta divided by 2 raised to n sin theta by 2 raised to n.
Exactly. Okay.
Okay.
Right.
So now we have to find limit of n tending to infinity bn.
Right.
Okay. So let this limit be equals to L1.
Okay.
So limit n tends to infinity bn equals to limit n tending to infinity b naught sin theta
By 2 power n
2
sin.
power n sin theta by 2 raised to n.
Yes.
Okay. So what we'll do is we'll arrange the terms. Okay. So we'll multiply and divide by theta.
Okay. So let's just go to the next page over here.
Okay. So moving on to the next step, we can see that
Right.
L1 equals to b naught sin theta into sin theta by 2 raised to n into theta and divided by theta by 2 raised to n.
Okay, let's just check what connection was there from the last page over here. So the last step here was that L1 was limit as n tending to infinity bn, which was what we derived as b naught sin theta by 2 power n sin theta by 2 power n. So the next step over here was that how did this theta come over here? How did this happen?
In the denominator, I took 2 raised to n below it.
Okay, so you multiply and divided by theta. Is
Yeah,
it?
exactly.
Right.
Okay,
let's
so
go.
theta by 2 raised to n tends to 0. Okay.
Right.
So we know that sin
Sin
x
by
by
x
x when
as-
limit x tends to 0
Yes.
equals to 1. So I am going to use this identity over here.
Right.
Since sin theta is b naught sin theta by theta is constant, so I can take the limit directly into the denominator.
Definitely.
So it becomes limit b naught theta into sin theta into 1 divided by limit n tending to infinity sin theta by 2 raised to n divided by theta by 2 raised to n.
Right. So you can write down the same this same limit as limit of theta by 2 power n tending to infinity of sin theta by 2 power n by theta by 2 power n.
Exactly.
Yes.
Okay, so now what I'm going to do is like I'm going to change the limit, which or we can if we want for a simplification we can take y equals to theta by 2 raised to n.
Right. So
and
as
the
n
limit
tends
will
to infinity.
become limit y tending to 0.
Yes.
Or else we can directly see over here this expression becomes 1.
Exactly.
Okay, so our limit becomes L1 equals to b naught sin theta by theta.
Yes.
Okay, so now substituting back the value of theta and sin theta, we can say that L1 equals to b naught square minus a naught square whole root divided by cos inverse a naught by b naught.
Okay.
So we actually use the expression now that A naught equals to B naught sin theta.
Right.
B naught cos theta to be corrected.
It's cos theta, is it?
Yeah, exactly. It's cos theta.
Uh-huh.
So we can say that cos inverse A naught by B naught equals to theta.
Okay, so that's how we got we substituted.
Yeah, and by
theta.
using Pythagoras theorem, we can get this one.
Okay.
So
perfect,
this comes our
perfect,
limit.
perfect.
Similarly, the applying the very same steps, we get L2 equals to the very same L1. We can prove that in the very similar fashion.
Okay. Perfect. So thanks a lot. So let's just look at the question again. So what did we use initially? We thought of this substitution as such: A naught is equal to B naught cos theta, which helped us pretty much. So what happened here was that we found out that there was a trend going on from A1, B1, A2 when we substitute this expression, right? So we went ahead and we found out the general form of AN and BN, and yeah, after that we remembered this formula which is pretty important, I'm assuming.
Exactly.
Right. So are there more such formulae which would be convenient if we remember them?
There are certain trigonometric formulas that will be taught in the trigonometric chapter as well.
Okay.
So whenever we have such trigonometric equations, we can use directly those formulas to simplify our equations.
Okay, brilliant. So we substituted, we after using this, we got down AN and BN to this particular form, and then limit of BN as n tends to infinity was considered as L1, and this was the expression. So let's go to the next page. So what happened in the next page is that we found out that we could get the expression in this form, in limit of x tend to infinity sin x by x form, because we know that it's equal to 1. So immediately we put that inside, and then we got L1 as b naught sin theta by theta, and from our initial expression we substituted and we used Pythagoras theorem over here, and we used the initial assumption over here to get the final limit as root of b naught square minus a naught square whole divided by cos inverse of a naught by b naught. And we also know that L2 will be equal to L1, and it's pretty much in the same fashion that can be derived. So yes, that was question number 30.